Hi and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the fifth part of the second video lecture on the introduction and underlying theory, and here we will non-dimensionalize the Reynolds equation. So let us start by clarifying on the independent, the dependent variables and the input parameters. Now here we have the time-dependent 2D Reynolds equation for incompressible and iso-viscous fluids, and we simplified the more general version that we saw before, in that here the surfaces are only moving in the x direction relative to each other. Now this is a second order PDE in terms of the dependent variable P, which is known as the hydrodynamic pressure. And obviously X, Y and T are the independent variables. Now it's also clear that input parameters must be surface velocities U1 and U2 and the ambient viscosity. However, what is perhaps not as obvious is that the film thickness function may be, or actually should be, treated as a dependent variable. Why? Because it may both depend on input to the problem and involve dependent variables in case we have deformable surfaces or other aspects that we consider, for example the force balance condition. So we need to treat it as a dependent variable. And we remember that when we scale only the independent and dependent variables, and the input parameters that will be part of the non-dimensional groups of parameters appearing in the dimensionless forms of the equations. So in this case we have independent parameters x, y and t, and the dependent one h of x, y, t and p of x, y and t, and the input parameters are the surface velocities u1 and u2 and the ambient viscosity. So we scale our independent and dependent variables just by reference parameters. We make them as general as possible and just call them x0, y0 and so forth. Then we can transform our dimensional form of the equation into the dimensionless form by this scaling. And here we go. So on the first line we've just introduced the scaling. On the second line we quickly realized that we can divide by h0. Okay, but from now on we have to do some assumptions. And we know by now we are free to choose the scaling parameter parameters as we like, as long as they have the dimensions of the variables that we scale. So in this case, if we have a bearing, we can, without loss of generality, choose y0 to be x0, at least if, as long as the bearing is finitely wide. And we can also choose the time reference parameter like this. We combine it with the average velocity of the surfaces and train and speed, so-called, and the reference parameter x0. Therefore, we can restate the dimensionless form of the equation in this way, and we observe that we can multiply by x0 everywhere, and we can rearrange the terms to get an even more simplified form of the equation. And finally, by multiplying with the term appearing inside the ddx and ddy Poiseuille terms, we can have the expression on the bottom here. And from this equation we can easily identify the one and only dimensional group in this dimensionless equation. Now, we typically know the length of L of the bearing, and in the case of a linear slider, as shown here, we also know the film thickness. And now I've been formulating this in another form. So previously we involved the angle, the inclination angle alpha, and now I have introduced an inclination parameter k instead. It is sometimes more convenient to present the equation in this form. So let us now use this information in the following way. We use as reference parameter for length L, and we use the reference parameter for the height as the trailing edge film thickness HT of the bearing. And we see that choosing P0 precisely as this expression, as identified above here, is a quite feasible alternative. Because for this choice we have now obtained an input parameter free dimensionless form of the Reynolds equation, and it looks like this. And we have obtained it under precisely this scaling. Now this means that if we solve this equation once numerically, it may be very tough, but it's hopefully not. But if we have done that, we can obtain all other possible solutions for a given value of the inclination parameter k, just by scaling our dimensionless variables back to dimension.